Next up, we've got Niharika from Mechanical Engineering.
Thank you. Hi, everyone. My name is Niharika, and I'm a PhD student advised by Dr. Kritika Manohar over in the Department of Mechanical Engineering. So I'm going to be presenting some applied work in collaboration with Idaho National Lab, which is mainly concentrates on nuclear reactors. So what I'm going to be talking about is data-driven modeling and sensing for nuclear energy systems. So let's start with some motivation. Why do we need real-time sensing and monitoring for energy systems? It's mainly because due to this energy crisis that we're going to face soon, we're moving towards integrated energy systems where you use renewables like solar, wind, with nuclear energy, with storage devices in order to sustain the industrial demand and the household demand for heat and electricity. So in general, the nuclear world is moving towards building advanced reactors. But we all know when we talk about nuclear, safety is of the utmost importance. Unfortunately, there have been some accidents with nuclear energy. Both of these accidents have taken place because of LOCA. So LOCA is loss of coolant accident. So the nuclear reactor has the core, which because of the neutronics reaction, there is heat that is generated. This heat is taken away constantly with the help of a coolant, and that's used to produce energy. However, in both these cases, the coolant immediately left the reactor vessel, and that is what caused like an increase in temperature, and that's what caused the accident. So the only thing that can tell us whether an accident is going to take place is monitoring your sensor readings. But you can't just go ahead and build a reactor and test it all by itself. So you keep doing testing, experimentation, modeling, and simulation. So our main work was using all of this data that you've generated, CAD models, computational fluid dynamic models, finite element analysis models in this virtual space in order to determine where should you place your sensors such that you don't just have information of those locations, but you know how to reconstruct the entire flow field in the best way possible. So this is a problem that has been solved, sparse sensing. But what comes into play in physical systems is spatial constraints. For example, the reactor vessel, the core, cannot take sensors. Or if you place a sensor there, you're going to have to change it in like a month because of reactivity and the temperatures that it would be sensing. So we have tried to take into account these spatial constraints in the design stage itself of our algorithm in order to place the sensors. So that's constraints, and we go to design. How have we done this? So what we need is data. So real-world data is available, but what we like to train on are computational fluid dynamics models, because you can run them for different powers, look at how each power perturbation creates your temperature field, and train on this kind of data. So the data that I have is for a test prototype that is used for detecting LOCA. So the red field is the heater, and all around it, the blue field is water that is circulating around the heater to take away heat from the heater. So we're trying to analyze how does this flow of temperature go with the help of sensors. So we train a reduced order model because the data that we have, it has like 40,000 data points, and I have multiple power perturbations. So if I wanted to select 5 sensors for this, the computation, like the combinatorial search would be infinite or really, really high. So we train a proper orthogonal decomposition model where we get our spatial modes on which sensors are placed. So the problem then becomes of how do we recover the POD mode coefficients A from sparse measurements Y. So we have our physics given by the data itself, and now the problem is looking at how do we discover the dynamics. We use a gappy linear estimator for this. So A hat is reconstructed with a simple pseudo-inverse, and we look at where should we place our sensors based on minimizing the error covariance between the true POD coefficients and our predicted POD coefficients from measurements. The criterion, the error covariance volume criterion is connected to de-optimal design and is the same as maximizing the log determinant of that covariance matrix. However, we want this to be extremely computationally efficient. So my advisor, Dr. Manohar, came up with this algorithm, came up with applying QR factorization in order to solve this problem. So in QR factorization, those 40,000 columns that we have each represent a location on your grid. So QR factorization chooses the column that has the maximal 2 norm, and this corresponds to this log determinant criterion, and chooses that as the first sensor location, or pivot in this case. And we continue our QR pivoting procedure from there. So how do we incorporate constraints into this? This is done in the pivoting procedure itself. So we look at constrained regions. So for example, in a region constraint, you cannot place a sensor in that constrained region. You can place exactly one, a maximum of one. Those type of constraints are handled by first placing sensors in the outside region, and then if we have a criterion of just one sensor in the constrained region, once you place that, you no longer look at pivots from that region, but you only look at pivots outside that region. So this is region constraint. Predetermined is when you have sensors already placed, but you want to optimize the rest. So you look at sensors from the set other than those that have already been placed. Similarly, with distance constraint, sensors should be a specific distance apart from each other, because the noise from the sensors they corrupt each other's readings. So in distance constraint, once you place a sensor, an epsilon ball around that sensor is constrained, and you only look at sensors outside that region. So we've done all of this, but we wanted to look at how far are we from the optimal set of sensors, or how far are we from the unconstrained optimal. So we have a random state space system here, where I have just 25 states, and I'm looking at picking 7 from these 25. So I can actually perform this brute force search for that log determinant objective, and this is what the histograms show. So the red star is the optimal. QR pivoting by itself with no constraints on the top is the black line. However, all of our region and predetermined constraints are quite close to optimal, so we can guarantee near optimal solutions in this case. However, to get intuition of how this would act on a real-world problem, we looked at propagation of heat through a plate. So there's a heater at 100 degrees Celsius, and we're looking at how does the heat propagate through the plate. And we have placed sensors based on different constraints. So region constraint, as you can see, has a higher error. This is because as the heat wave propagates, they correspond to the Fourier modes. So generally, sensors are going to be placed where the Fourier modes are located. So if you remove sensors from near the heater region, you can see a definite increase in the error in that region. So especially for safety critical systems, moving around your sensors or placing them in a different configuration, it is important to know how would you quantify your reconstruction errors. Similarly, we also look at if there's noise in the sensor readings, how is that propagated into the state reconstruction? So the expectation of that state covariance, we look at the standard deviation of that, and that is what is plotted on the plots below. So for each of our constraints, we can show how error in measurements will get propagated into state reconstruction. So it's easy to quantify that when you remove sensors from close to the heater, your uncertainty in readings in that location is higher. Now that we've done all of this for the test cases, we look at the prototype that is used for LOCA detection. So as you can see, the random sensors is sensors placed by intuition. Those always have a higher reconstruction error for all of our different power perturbations. Unconstrained and constrained QR are comparable. So we concluded that random sensors would give you low accuracy, but constraining sensors outside the heater region could still give you higher accuracy. In the end, we again looked at how noise propagates into the state reconstruction, and similarly, with moving sensors outside the heater region, you can see a higher band of uncertainty appear in the reconstruction of the heater region. And in the plot on the right, we have shown how different ways of selecting random sensors for increasing number of sensors would still give you the same band of errors. But with QR pivoting, choosing sensors in a way that's optimal would reduce your errors by the more number of sensors that you select. So you can make like an informed choice of sensors versus accuracy using our method. So in conclusion, we wanted to conclude that sensor-based reconstruction enables real-time monitoring of temperature fields, as we have shown, and we have also looked at uncertainty estimation. This has been done in a linear fashion, so the next steps would be to maybe develop nonlinear sensor placement methods and even analyze what power transient caused this kind of temperature field from just sensor readings. Thank you. Yeah.
Can you see the previous slide, please? That's so, the constrained one, I thought that would be better because you're spreading them out a little bit more, but looking at the uncertainty map, it seems to be worse. Right?
Yeah, so in the constraint one, as you're moving sensors away from the heater region, the uncertainty in that heater region has increased because you don't have a reading from there.
But you would prefer the unconstrained one in this case?
Yeah, but in cases where you absolutely cannot place a sensor there, you would do it with the constrained case, but you can quantify the uncertainty that arises by moving your sensors out of that region.
Okay, thanks.
And I'm just curious, there's some asymmetry to where the optimal placements are. What's causing that? I mean, it seems like, oh, I've just got this heating thing and then water. I would expect to see it somehow balanced out, but.
So it's water, but it's advection currents that are set up as the water propagates through the, like you're trying to analyze like there's a reactor and how would the coolant circulate through it. That's the reason, yeah, sorry, thank you.
I have a question.
Yeah, of course.
So when you did POD to get like a basis of the dynamics, and then you use that basis to then do de-optimal design on. You did an error analysis for like state estimation. Do you have any error analysis for like how that decomposition has some errors in it and it's not perfect? How those errors go through this whole process?
Oh yeah, so my colleague Andre Kushin is writing a paper on exactly that. We see this like double descent phenomenon in the error as you increase the number of sensors. So that double descent, one of the factors is due to the error in the POD decomposition, like the decomposition itself. So that should be coming up sometime.
Thank you.
Thank you so much.